ఏం రావట్లేదు ఏం రావట్లేదు
ఇప్పుడు వస్తుంది.
ఏ మైక్ కనెక్ట్ అన్నా కదా ఇదే మైక్ వాడతారు
ఓడియం వైర్లెస్ నడుస్తా అన్న వైర్లెస్ పెట్టినాను వాయిస్
డేట్ ఒకటి డాక్యుమెంట్స్ ఇస్తారు
నేనే పైకి వచ్చాను. అది బోర్డు వాడిని కావట్లేదు అమ్మా. అది ఎందుకు అది ఎవరికి కనిపిస్తుంది అందరూ క్లారిటీగా.
Okay, can I move now?
हाँ सर यू कैन पर इधर से चलना है सर कैमरे पे.
Then I should use this only. Why you use?
हाँ वो भी चल.
Okay. Or I can use this key also. ये तो श्री I will keep this here. So good afternoon and welcome to the next session, afternoon session of the GAN course. So hope you have all a good lunch, and after so much interesting energetic lecture, okay, so my job is to keep you awake also. So after this we have nice sweet, okay, the sweet selection all done by our volunteers. So thank you. So what we'll see is overview of inverter and its control for PV system. So before we plan for the sessions, various sessions, we had a meeting with Professor Pota, online meeting. Then we decided, he decided what can be the course contents and all. So this course is more about the understanding of the things related to renewable energy, smart grid, integration, interface. Okay. So I have selected this topic for you. So let's have some understanding on the inverter. Okay. So we know inverter. Many of you are the faculties here. Many of you are already working in the field. Like Uday sir is there. He's installing so many power plants, solar PV power plant. And many of you have simulated some system as a PhD scholar, MTech scholar. So I may be presenting something, but you may have some inputs to share. Okay. So please share that also. Okay. So it will be more interactive. Okay. So I have started with some things related to inverter interface and what exactly the inverter is. Okay. So from my point of view maybe, okay, but something you want to contribute, you please say something. Okay. So the overview of inverter and its control for PV system. So we'll see the configuration of inverter for PV integration, then topology of PV interface, then particularly we'll see the selective harmonic elimination. Like we know the control of inverter, there are various PWM techniques available. Can you know any PWM technique? Can you say any PWM technique? SPWM, sine triangle PWM, okay. Then your space vector PWM, very difficult to at least simulate, understand, We have the course PWM techniques. We run the course, elective course, PWM techniques in power converter. So another technique is selective harmonic elimination. We select the harmonic and we eliminate that. Okay, that is selective harmonic. So three-phase PV grid connected inverter control that we'll see. So some of the contents majorly taken from the various sources just to understand the basic things. That projector is not turn on, that projector. So one thing is central inverter. So when we have, is it okay if, because that is, so how to interface the PV inverter, PV system to the grid? Okay, so one of the way you connect all the panels, PV panels in a one string in one row. Okay, have many such strings connected in parallel and connect one inverter. Okay, and that inverter can be connected to the grid. Okay, so that is called as central inverter. So it is only one inverter in one system. The range may be for 10 to 250 kilowatt rating, three phase. Then several strings are connected in parallel. High efficiency because one inverter has to be managed, low cost. But what is the problem? No optimal MPPT. MPPT is maximum power point tracking. Okay, so when we are tracking the maximum power point, okay, so you cannot track as a complete array. Okay, you can, if it is a one panel, you can efficiently track the MPP. If the panel number is increased, then it's very difficult to track the MPP as a combined one. Okay, then you have, of course, you have several panels. Then again, getting the MPPT point is difficult. Low reliability because if inverter goes, something happened to inverter, then again there is a power loss. You cannot feed the power to the grid. Okay, so low reliability. So then we have another system in which string inverter means each string carries one inverter. Each string carries inverter. So in the previous case, you have only one inverter and all the strings are connected in parallel. Okay. If you have any question related to any component in the system, please ask. Okay. Like you have the diode here. Okay. So this diode is there to should not flow the reverse current. Okay. That is a blocking diode. Say there is also bypass diode. Okay. I think Professor Kulkarni will clear about that in his own session. So the string inverter in which we have the each string carries one inverter. So all the inverters are connected to AC bus. Okay, so we have multiple inverters. So reliability of course increase. If there is one inverter failure, then there is no chance that complete power will get cut off from your to feed to the AC grid. But you have to maintain 3 inverters. Okay. But of course the MPPT is better because for small string you can actually maintain better MPPT, maximum power point tracking. Then here what you observe is one DC-DC converter is connected in between one string and then you have collectively one inverter. So this DC-DC converter is again maintaining the MPPT of each string. Okay. So, and then inverter is there to feed the power. So there are two streams for the string inverter. Okay, one is a direct inverter and one is a DC-DC converters to each string, and then collectively you have the inverter. Then you have directly module connected inverter. You have the module and there is a inverter behind that. Okay, and directly connected to AC grid. So these are also available in the market. So very low rating, 50 to 180 watt. Each panel has its own inverter enabling better MPPT also. And then though more inverters. So each inverter, if you combine the efficiency, of course the combined efficiency is low, difficult to maintain, and low cost per kilowatt. Each cell has its own MPPT. Then it is right. Like each panel has its own MPPT. If you have two panels, then combined MPPT is different. Combined power is different. Yeah, and then you have the bypass diode, which is so if you want to have shadow effect, then you have to bypass some panels from the system. Shading effect is there. So this is your MPPT. Power versus voltage. If this is a one panel MPPT, if you have several panels connected in series or parallel, okay? So we have the scale may be different. Okay? Scale may be different, and then each panel actually you have connected in series, but there is one bypass diode to bypass this. If there is some shading on the panel, so that panel has to be bypassed. In that case, this nature of the characteristic will change. Okay, and there can be some kind of peaks, more peaks like this, local minima. So these problems may also arise. Okay, and very difficult to track the MPPT then. It will be difficult to track the maximum power point tracking, because most of the algorithm work on the principle of tracking the maximum power point where you are. So this is your P and this is your V. So this is your, at this point, the dP by dV is 0. Here dP by dV is positive, and here dP by dV is negative. So it has to track this point. But here also it generates a situation like dP by dV is 0. Here also it generates a situation like dP by dV is 0. Okay? So it will get confused. Okay? It will get confused. So such problem, this is one of the problem. But there can be a many problem to better track the MPPT. If it is a small system, you can track it efficiently. If the panels are spread in a huge area, okay, it's difficult to track. Okay, and there are so many MPPT techniques that are coming, and the basic techniques are like you have to track one small solar cell, okay, and you can utilize that to simulate the entire things, this entire power plant, okay. But situation what the actual cell is receiving, the radiation that is receiving by one cell may be different than, or some situations may be different for the entire plant and the cell. Okay, some panels are not get clean. Some birds are sitting on the panel. Okay, some shading of the pole or shadow is coming but not getting on the reference cell. So it is not a correct representation of just cell is representing the complete power plant. But you have the systems, there are so many techniques. There are some modified AI based, ML based, machine learning based, optimization based techniques. So many techniques are there, and you'll get so many papers related to MPPT. Also, there are some problems to sort out these issues also, like local minima, local maxima and local minima. So this MPPT problem, if lower number of panels are there, so you have better MPPT. If number of panels are increased, then you have to find a proper way to deal with.
String inverter, multi-string. And how does that we have utility scale power plant. You have a 750 megawatt ground mounted. In that case, can we have option of having one string inverter for two strings?
That is also possible, sir.
Otherwise, this number of string inverters will be
That permutation combinations may be there.
one inverter.
So 2 string, 1 inverter.
What is,
That is.
you have to see recommendation. Like this.
So this optimization you have to done for plant by plant basis. Maybe for one plant it is that is a solution. Another plant that may not be a solution. Depending on the geographical location also you have to study that plant. So one solution for one plant may not be applied to the other plant. So all plants may be depending on the solution. Maybe hilly area is there sometime. So panels are based on the hilly area. Somewhere in the VNIT we have the all rooftop system. We have 1 megawatt generation in our campus. Yeah. So Shravan Kumar is there. He's in from electrical maintenance section. So he can tell you about how many power plants are there. Means combinedly we have 1 megawatt. And then reference, it is connected to grid. Okay, you are want to ask this how you generate it. So there are algorithm, man. Okay, so it has to detect this thing. So it will sense this point, this point. Okay? So what is the power here? What is the voltage here? Okay, sorry. Okay.
For a string, this curve which you want for string. Total string.
So total string PV curve.
Where
See-
voltage gets added.
No, we don't generate that kind of PV curve. We don't require that PV curve. Only thing we just sense the voltage and the current, and we give that value to the MPPT algorithm, okay, and which will sense the initial P and this here P1 and P2. This V1 and V2. Okay, so it is changing from 1 to 2. So it is sensing this means it is going away from the MPPT. Okay, so this point, I want to achieve this point. I want to achieve this point. But I'm going away from the MP point. So I have to increase my voltage. So I will give the reference such that that voltage should increase. Okay, so that I will achieve this point. So I will always try to track this point. So that
Algorithm.
so I have to track this voltage. If I track this voltage, I will track this point. Reference voltage you have to track. Okay. So reference means this voltage. Now the radiations will change. This may be like this. Radiation temperature may change. Okay. So all this situation you have to always track the maximum power point. String, right. String current will be same in string because it is connected in series. Okay. So your question is answered, madam. Each panel also PV curve. Right. Right. It will be big, madam. It will be. If I want to obtain that, what is my question? Yes. Yes. So don't. That is not required to obtain this curve. That is what my answer is. Okay. So what I will always track this point P1, P2. This is my at T1 instant. This is my at T2 instant. Okay. I will see my power is decreased or increased. Initially I am lying here. Now I am lying here. So I am going away from that. This is what one of the algorithm that says like this. That is hill climbing algorithm. So I have to track this point, but I am moving in this direction. Okay. So I will increase my reference voltage so that I will track this point. Okay. So I have to always track this point. Okay. So actually there is no requirement of any reference cell also. Okay. Because you can directly give the panel voltage, panel current, and you can track the MPP. Okay, you can give that value to the algorithm, and that will be properly track the MPP. Reference voltage, yeah, at one point you have this voltage, okay. Now you know the difference between this value, okay, and this value. So in the previous reference voltage, you can add that much voltage, okay. In the previous reference voltage, you can add that voltage so that it will track that voltage. Okay? It will go step by step, okay. Algorithm is maintained in that manner, okay. So they have, how you increase the voltage in this maybe simple DC-DC converter, you increase the duty ratio, okay. So by a small amount, you will increase the duty ratio, like P equal to, this is your duty ratio, increase by small incremental way. So your point is here, so it will increment in this fashion, okay. It will track this point, okay. So it may take some time also, okay. It may take some time. If you have more this size of iteration, okay, is more, then you can track it very fast. Okay, if it's small, then it will track somewhat larger time. Okay, so there are fast tracking and slow tracking algorithms are also there. Fast tracking is required when, like, you are installing the panels on some vehicle. Okay, then you require to have very fast tracking because some shadow comes and immediately go. Okay, vehicle is moving from the unshaded to shaded area. Okay. So every time, so but for stable system, you may not require that much fast tracking. But if it is a fast, it is good. Okay. Then yeah, MPPT we can discuss more maybe if we get a chance. Okay. I had a slide MPPT. I just removed that slide so that I focus on this. But we can discuss a basic at least MPPT technique if we get a chance. But we have some problems, tutorials based on MPPT. Okay. So topologies of PV grid interface, in which you have the isolated topologies like low frequency transformer using high frequency transformer, then non-isolated transformer, transformer-less inverter. So there is no transformer in the system. And then it also categorized in terms of 3-stage, 2-stage and 1-stage. And depending on the control system, scalar control and DQ axis control. We are using DQ axis control, not the scalar control, but we'll look into that also. So let's see what is the isolated topologies for with a low frequency 50 Hz transformer. Low frequency means our normal conventional 50 Hz transformer. And let's see the number of stages. So this is simple, just to understand, may not be exactly implementable. This is taken from the one online course provided by Professor Alumanan from ISC Bangalore. Very nicely designed course on the designing of photovoltaic system. So this is the PV array. Then you have the MPPT. Okay. Do you have pointer? Okay, it's okay. So this is your MPPT, second block. There is simple DC-DC converter. Okay, to track the system, and then then you have another DC-DC converter. So what you want? You want the waveform to be in the sinusoidal shape. Okay, so you have another DC-DC converter in which you can make the, so what the previous converter will give you, a straight, not a time varying component, the steady state. Okay, so this is the first DC-DC converter will give you. Second DC-DC converter will give you the like a half sinusoidal waveform. Okay, so reference that we are giving to the inverter is, thank you. So reference to the inverter that we are giving to the second is like a sinusoidal. So it will generate the output like this, and then you have the unfolding circuit in which you can first have this kind of waveform, and then in the negative you can produce like this. So this will get inverted in the second for this duration, and it will become sinusoidal. Okay, it's not much practical, but it is a 3-stage kind of system. Maybe for the low application, low rating application, this can be used. Okay. And then you have LFT, that is low frequency transformer to isolate it. Then you have the inductor for filtering. And then you are connecting it to line and neutral, in between line and neutral. Then two stage, okay. In the two stage, you have the, again, one DC-DC converter for MPPT. And then you have the inverter, okay. And then you have the low frequency transformer. So there is no like a unfolding kind, folding kind of circuit, okay. So you have the edge bridge inverter, simple edge bridge inverter. You know the function of edge bridge inverter, that these two switches are on, you will get a positive. These two switches are on, you will get a negative. Okay, so you'll get a pulsed waveform actually. Okay, so what is the output? You will get a pulsed. Okay, at the most you can produce square waveform. Square waveform. So can we have square waveform? We can have, I think the Chinese inverter, they are, sorry to say, but they get, if you observe the waveform across it, it is a square or triangular waveform. Okay, one of the inverter that we have one in, I think Professor Chaudhary gave me, that we observe the waveform, it was just a triangular waveform. Okay, but our normal appliance can work on that. I observed that the tube light was working nicely, but it keep producing some humming sound. So we have simple inverter, you can produce square wave, some appliances may work. Okay, heating appliances, of course, it will work. So square waveform means more harmonics. Okay. So the technique that we use here, we generate a pulsed waveform. Okay, not exactly square. So we generate a pulsed kind of waveform. Like this. Pulsed wave. So what is the advantage of pulse wave that we are going to study in the selective harmonic elimination? But edge bridge inverter produces a pulsed waveform. Okay, depending on which switch is on and off, it can produce a zero voltage. Okay, if upper two switches are on, okay, if upper two switches are on, it will generate zero voltage across. This is your load, means it is connected to the grid. Okay, so A and B point, this is your A and B point is connected to the grid. So if you turn on these two switches, okay, so this will be your zero. Okay, so the potential of A and B is same, so it will be zero voltage. Then you have the isolated topologies with high frequency. Okay, now we have the low frequency transformer here. We can shift into the DC-DC conversion state. That becomes the high frequency. So what is the advantage? Advantage is that we are getting, so what is isolation means? You are not connecting any part electrically to the grid. So this is your PV system and this is your grid system. Okay, so there is no any direct connection, electrical connection between the two, PV grid and your PV system. That is meant by isolation. Okay, so that can be obtained with the high frequency transformer also, in which you have a DC-DC conversion state. You have the high frequency transformer. So first there is a inverting waveform that you are obtaining. Then you have the high frequency transformer, and then again you are rectifying that. Again you are rectifying that. So you get DC here. So here is also a DC. Okay, and after here is also you are getting the DC. So only stage in between, or you can have the boosting in also. The boost voltage you can also obtain this. Okay, there are two purposes for MPPT. One is that you can MPPT converter. You can also boost the voltage. Okay, with the help of boost converter. So you can have the isolation with the help of high frequency transformer. And then you have the inverter, and that may be directly connected to grid. Because you have already provided the isolation, so there is no requirement of another isolation now. Okay, with the help of low frequency. Okay, even you can obtain the higher voltage by properly choosing the turn ratio of the high frequency transformer. So you can also increase the voltage. That is also another advantage. And another advantage that you will make a system compact, because high frequency transformer means it is very compact as compared to low frequency transformer. Okay. Yeah, so you have two power stage. isolated with high frequency transformer. Same thing what it's shown. So this is your high frequency transformer, completely DC to DC with high frequency transformer. So you have the inverter stage and you have the rectifier state. Okay. Sorry, it is. Yeah, then you have the topologies with a low frequency transformer, single power stage with a low frequency transformer. So you don't have a DC-DC stage, just inverter. Okay. Then you have three phase also. So this is a single phase, this is a three phase transformer. Okay, it's connected to three phase transformer. Okay. So this is your single phase. So we'll more focus now on voltage source inverter, that is edge bridge inverter. So what is the operation? Is simple DC source, okay, across volt A and B, okay. So these are A and B point. So voltage VAB, we write VAB. Okay, if these two switches are on, okay, S1 and S2 are on, we get a positive plus VDC across this. If these two switches are off and these two are on, S3, S4 are on, then we'll get a negative voltage. That's what we understood, a simple inverter. Okay. But there are two techniques, that bipolar PWM and unipolar PWM. Okay. So bipolar PWM, you will not find any zero state. Okay. So what are the two states that I described? When these two are on, it is a positive plus VDC. VAB is plus VDC. If these two switches are on, if it is minus VDC. So here VAB is very between plus VDC or minus VDC. When S1, S2 are on, and here it is S3, S4 are on. Then you can also have VAB can be 0 if S1, S3 are on, correct? Or lower two switches are on, okay? Or even S4 and S2 are on, okay? You will get a 0 voltage. So,
high frequency transformer, what the frequency is going to be?
in terms of kilohertz, kilohertz.
So that reduces the size by what, 20, 30 times?
I think it is how the frequency and size related dimensions. I think there is equation, okay? So we have.
Just that omega phi m, right?
So we have equation
omega phi m.
4.44 at phi. That is the equation of transformer.
Yeah, voltage, right? That's
And
correct.
this flux means your flux density is
Much lower.
upon AI. So if I write into the flux, it is A into B. So your frequency is, so this is the area, the core size will inversely proportional to frequency.
Frequency. So you've got kilohertz, so it just shrink by
It
factor
will
of
shrink.
20.
Yeah. If it is 50 hertz and you compare 50 hertz and kilohertz, it will be much reduced. So size will be reduced. So A is the core area. So core area itself will get reduced. Okay, for the same voltage. Okay, so naturally the size will be very much compact. Okay.
What about number of turns?
Number of turns can be same because you have to maintain the voltage same maybe. But again, it depends on the what voltage you required at at a DC-DC stage. The requirement of that voltage may be different than the requirement of what exactly you require the low frequency transformer.
Yeah, that's fine. So the ratio is decided by what you need.
Yes.
The number of turns, because no load current,
Yes.
So no load, get the right no load current, you choose the number of turns. So I guess the number of turns also will go down, right?
Number of turns will go down.
Because the same turn can produce much more flux. So the multiplied by F.
F. Right. But again, we have to, it is a choice because we have to boost the voltage also sometime. So secondary of high frequency transformer, we have the more turns as compared to primary of the transformer.
How common are these configurations?
These are very common actually. Yeah. So to make the inverter very compact, we use this. Very much economic because it's taking very less space as compared to low frequency transformer. Low frequency is very huge transformer, very bulky. Weight, efficiency also reduced. It is economical. Maybe complex, but maybe complex.
The same magnetic material as you use for high frequency?
No. Magnetic materials, I think ferrite core is there.
There are different types of cores.
Different type of cores are there. Any more core do you name other than ferrite? CRGO. Okay.
But more expensive?
Yeah, they are expensive. Depends on the availability also, because if you compare the availability in Nagpur and Mumbai, maybe in Mumbai it is better, easily will get. So there are two techniques, especially we discuss like a bipolar PWM and unipolar PWM. So let's compare these two techniques. So what these techniques are? Bipolar means, as you told, sine triangle PWM. Okay, in sine triangle PWM, we compare one sine waveform and a triangular waveform, and to generate this curve. Okay, you open it from directly from the net. Have you downloaded? Why it is looking so unclear? Okay. So we have a VAB. So the third waveform that we have VAB, which varies from is a pulse waveform. Clear? 200 to minus 200. Okay. So that is a bipolar PWM. There is no zero stage. Okay. There is no zero state here. Okay. Either you can have 200 or you can have minus 200. That is a bipolar. Okay. Unipolar means you have on zero state, but you require so unipolar you require two sinusoidal waveforms phase shifted by 180 degree. Okay. And if you compare the sinusoidal triangular waveform with these two waveforms and apply the logic, so what you can get is for positive half cycle, you will get a positive and zero state, 200 and 0. And for negative half cycle, you will get minus 200 and 0. Okay. So you can produce this kind of waveform. So which is the better technique, unipolar and bipolar? Okay. So before that, why we need a PWM? Okay, so as we discussed that we can have the square waveform, okay, but we are producing a pulsed waveform. Okay, so we can modulate the pulse. Why we want to modulate the pulse? Because we want to control the fundamental. Okay, we want to modulate the fundamental from, let's say, minimum to some maximum value. Okay, and as well as we want to suppress the harmonics. Okay, so the beauty of the waveform, if you select a particular waveform, the particular symmetry or particular shape of the waveform, automatically you can suppress some harmonics. Okay, so for that we need to know the nature of the waveform and how to model it or how to analyze as a Fourier series. Okay, so why we need PWM? To control the AC side fundamental voltage and mitigation of harmonics, because harmonic current increases the losses, increase the torque pulsation and increase the core loss. Okay, so the effect of harmonics. We want to reduce the harmonic, but we want to retain the fundamental. some effect of harmonics, the additional copper loss due to harmonic current, increased core losses, increased electromagnetic interference with communication circuit, and then increased dielectric stress on insulation, electrostatic interference with communication circuit, resonance between winding reactance and feeder capacitance. So voltage harmonics supplying light circuit can cause fluctuations of light intensity perceptible to the human eyes, and of course torque pulsation in motor. So that's why you want to avoid the harmonics. Okay. So let's discuss about the selective harmonic elimination. So one of the method that you select the harmonic and eliminate. Okay. So which type of harmonic you will select? Will you select the lower order harmonic or higher order harmonic to eliminate? Lower order harmonic you will eliminate. Okay. Why? Why more disturbing? High magnitude. Okay. They are high magnitude in nature. Filter design is complicated, right? Okay, because they are high in magnitude. Okay, so you'll eliminate the lower order harmonics because magnitude is high. They will produce the more current, which is more harmonic current. Okay, higher order harmonics, the magnitude itself is low, so not much problematic. Okay, and then why particularly this method can be selected? Why not only the sine triangle PWM? Why to discuss this selective harmonic elimination? Okay. Particularly in higher power application, the harmonic content of the output waveform has to be reduced as much as possible in order to avoid distortion in the grid. Okay. Particularly for high power application. Okay. If you are for high power application, if you are going to use the sine triangle PWM, that will generate the huge loss in terms of switching losses. Okay. So better you select the selective harmonic elimination, which is of somewhat lower frequency. Okay. And why to again see every system has to be compact. Okay, if you have more switching losses, then you increase the heat sink area. Okay, there is always a heat sink at the power electronics, that circuit or switches. Okay, so more switch loss you have to provide bigger heat sink that will increase your size and weight. Okay, so you will not be in market competitive market. Okay, you have to reduce the size cost. Okay. So always you have to trade off between this. So we know the simple Fourier series, first year maths. Okay. Even maybe you have studied in the signal systems. Fourier's any periodic waveform can be categorized into a DC source and cos and sinusoidal waveform, combination of cosine and sinusoidal waveforms. So what is waveform symmetry? Now we have the even function, odd function, half wave, even, quarter wave. So what it mean for us? So even function is if you go a little bit same distance, if you have small time t here in the positive direction and in the negative direction, the value of function is not changing. That is an even function. Okay. What is odd? Odd is if you are going same distance positive side, same distance negative side, magnitude is same, sign is different. That is the even function. That is odd function. So we generally work with odd function, okay, like sine. So all sine terms that we use, okay, what we write current as Im sine omega t, V as Vm sine omega t. So it's easy to interpret, easy to handle, okay, easy to understand. Then we have half wave symmetry. What is half wave symmetry? Is if you go a little bit a distance t by 2, okay. So ft is this, and then if you go little bit here, okay, so that will become negative. Okay, so here is positive, this is your negative, that is half wave symmetry. So if you have half wave symmetry, generally we have half wave symmetry, and then what your analysis or your computational will reduced. Okay, then you have to integrate only for half duration. Okay, so here when you are calculating the function, you are integrating for a complete time period. Okay, 0 to t by 2, and here you are only integrating for 0 to, yeah, it is I think 0 to, or you can integrate only for half time duration. Okay, that will give the value of your coefficients. Then you have the quarter wave symmetry. Okay, 1/4 of the waveform. Okay, so 1/4 of the waveform. Then again you have to integrate for 0 to t by 4. here. So the analysis will reduced. Okay. So this is a odd quarter wave symmetry. Yeah, this is all about the summary of waveform symmetry. If the function is DC offset, A0 will be non-zero. So if you have superimposed DC, okay, so that A0 is non-zero. But if there is no DC component in the waveform, A0 is zero. If the signal is even, all the B terms are zero, no sine components. If signal is odd, all A terms are zero, no cosine components. If the function has half wave symmetry, then all the even coefficients are zero, and we only have to integrate half the signal. So even coefficients are zero, means even harmonics are zero. So 2, 4, multiple of 2 is 0. Okay. So if you maintain the half wave symmetry, automatically the harmonics content of the even harmonics will automatically reduced. Okay. So we don't have to care about the even harmonics. So what we care about the odd harmonics, 3, 5, 7. Okay. Then if the function has quarter wave symmetry, we only need to integrate quarter of the signal. The Fourier series of sine, okay, we'll not discuss much of this, but yeah. So this is also a small inverter in which just generally in the BTech course, the first year power electronics course or the first course in power electronics. So inverter is studied in this with this circuit, that we have the two switches, the two sources. If we turn on this switch, the voltage is positive. If we turn on the bottom switch, the voltage is negative. So we can generate the square waveform. So what is square waveform? It has a 33% of the third harmonic. Again, it has a odd symmetry. It has a half wave symmetry. So no 2 and multiple of 2 and multiple of 2 harmonic or even harmonic, no even harmonic. So automatically we have omitted even harmonic. So what we want to care about the third odd harmonics. So it has a 33% of the third harmonics. How to eliminate the third harmonics. Okay. So to reduce this percentage, it is necessary to add the AC filter, as someone told about the AC filter. Yeah, you told about the AC filter. The filter that can reduce the third harmonic voltage to within the specification usually is large and heavy. If you want to try to eliminate the lower order harmonic with the help of filter, okay, the filter size is very big. Okay. Okay, let me show you the waveform. So this is a simple square waveform. Okay. Srinivas, you just circulate. They will move it, no problem. The waveform has half wave symmetry and quarter wave symmetry. So this square waveform consists of fundamental waveform, as you see here. This is a fundamental, third harmonic, fifth harmonic, and so on. Infinite harmonic. If you add this all harmonics, you will get a square waveform. Okay. So if you have the fundamental harmonic, you have the you have the third harmonic, you have the fifth harmonic. Okay. So all these sine waveforms together make your square waveform. Okay. So square waveform, no control over the fundamental, and there is no control over the harmonic. Even you cannot control the fundamental. Even if you do, you may not control the harmonic also. Okay. Then little change that we have done is in the positive half cycle you have one more switching. Can you identify that? As compared to this, you have one more switching in the positive half cycle as well as in the negative half cycle. But the symmetry is maintained. What kind of symmetry? Odd symmetry, half wave symmetry, and quarter wave symmetry. Okay, without doing much on the symmetry, we have just switched one more time in positive half cycle also and negative half cycle also. So what it gives us? This kind of waveform at some alpha distance. Okay, at some alpha instant you have done this. Okay, or at some alpha angle. Then if you try to calculate the fundamental, okay, or any harmonic component, okay. So this is your equation for harmonic components. So what was the equation for, so it is a 2 VDC by pi, okay. That is your VM, this is your VM for the fundamental. VM is maximum voltage. We write VM sine omega t, okay. So this is that VM, 2 VDC by pi, okay. So this is a VM for third harmonic. This is a VM for fifth harmonic, okay. So now your VM is changing to this, okay. So now by controlling the angle alpha, you can have the control over the fundamental or harmonic, okay. Either you can control the harmonic or you can control the fundamental, okay. So you have alpha, you can vary from, if it is alpha is 90, just like a square waveform. So if alpha changes from 90 to 60, so VRO changes from 1 to 0. So for 90 it is 1 per unit and 60 it is 0. Okay, 60 it is 0. So you can change your fundamental from 0 to 1 per unit. Okay, you can change your fundamental from 0 to 1 per unit. So what we achieved with this? Only one control variable alpha. We can choose the value of alpha to produce desired fundamental waveform. Okay. So generally we used to control the fundamental. Okay. So harmonics we are getting in additional. Okay. But there is no control over the harmonic. Okay. So what to do? We can have another 2 angle switching. In 2 times I switched in 1 half cycle, in 1 quarter cycle. Okay. In the previous case, in 1 quarter cycle I am switching only once. Now I am switching twice. Sorry. I am switching twice. So I have 2 angles. I got, if you apply the Fourier series, I will get this equation. Okay. Now I can have 1 fundamental, 1 harmonics. I can write 2 equations. Okay, I can solve 2 equations and I can solve 2 unknowns with the 2 equations. So I can have the perfect control over the fundamental and at least I can reduce the first harmonic, let's say third harmonic. I can reduce, suppress. Okay. So I can write the equation for fundamental. I will write the equation for third harmonic. Okay. So this is the, yeah. So I can write the equation for, here it is written for third and fifth harmonic. Okay, not for fundamental. Just for example, the equation is written for third and fifth harmonic to be 0. And what we get is alpha 1 and alpha 2, this angle. Okay, so you can see the third and fifth are getting 0. Third and fifth is getting 0. Okay, with this angle, if we select, okay, it is not a simple equation. You require some advanced mathematical tool. Okay, to solve these the transcendental equations. Okay, maybe some optimization method, or you can have several equations. Okay, if you have, yeah, then we have, okay, then if it is a 3-phase voltage source inverter, in the 3-phase voltage source inverter, again we have another advantage that you don't have the third and multiple of third harmonics. Okay, so they get cancelled out. Okay, so third, sixth is always not there, is even harmonics. So 9th is not there. Okay, 15 is not there. Okay, so all these harmonics eliminated in the 3-phase inverter. So you have to worry about the 5th and 7th. That is the first harmonic that you have to worry about for the 3-phase. So if you apply alpha 1 and alpha 2, okay, so this is your alpha 1 and alpha 2. And the black lines that you see, these are counters for your fundamental voltage. Okay, so fundamental voltage varies from 0 to 1. Okay, and if you want to have the fundamental voltage at somewhere here, and if you eliminate the 5th harmonic, okay, so you have to have your alpha 1 this, alpha 2 this. So appropriate selecting alpha 1 and alpha 2, you can select appropriate fundamental voltage as well as you want to reduce the 5th harmonic. Okay, then green is for 7th harmonic. Okay, then if you want to eliminate both the harmonics, okay, so you have to work somewhere here. Then your fundamental voltage has to be here. That eliminate both fifth and seventh. But always it is not possible that you have to, your system need always this voltage, fundamental voltage. Okay. So you have the, somewhere it is not converge also. If you, anytime, anywhere we cannot have the both harmonics to be 0. Okay. So this cannot be solved. Okay. At this point, 7th is 0, but 5th is not 0. Okay. If you select these two, excuse me. If you select this 2 point, if you select this point, okay, you will not get any solution for 5th harmonic because 5th is not 0 here. Okay. Or if you try to solve it, you will not arrive at some solution. Okay. Your solution will not get converged in terms of optimization language. Okay. Then you have n number of switching, m number of switching. Okay, like we have seen 1 angle switching, 2 angle switching, and this is a generalized equation. Okay, the generalized equation for the fifth for the. So then you have, let's say you have 3 angles. Okay, you can control over the 1 fundamental and reduce the 2 harmonics. Okay, so likewise you have m number of switching, so you can, the fundamental you can control, and m minus 1 harmonics you can eliminate. Okay, so this is given by very, very old paper, 1977 paper. Okay, but still you will find a paper on selective harmonic elimination till date. Okay, if you select the paper, or if you search the paper, you will get some paper on selective harmonic elimination. Okay, this is the first paper maybe by G.S. Bhuja. Sir, he came here for GAN course also. The first GAN course he only delivered here. Yeah, G.S. Bhuja. So I think he has introduced this selective harmonic elimination. Very nice paper to read. So you have the m number of switching, and you can eliminate the m minus 1 harmonic, as well as you can eliminate you can control the fundamental. So these are the 1 and 2 angle switching for alpha 1 and alpha 2. If you see the values of, this is just the problem given for maybe for exams, because we run the course PWM techniques for power converters. So here for the 2 angle switching, we reduce the 5th harmonic 0, negligible. 7th is also 0. 7th is also 0. Okay. Then this is the case when your 5th and 7th again 0. And here 5th, 7th, 11th, 13th, 17th, they are 0. So you'll have to have almost 5 equations. You have to solve. 5 unknowns, you have to get the values of 5 unknown. So you have to use some mathematical tool. Mathematical tool work here. Then you have so you can solve for any waveform, because you can produce a 0 voltage. If it is a 3-level inverter, you can produce a 0 voltage. Okay. In that case, again, your angles can be changed for getting different values of fundamental and so this is your for 3-level inverter. Okay. 3-level means you are having the 0 level also. Okay. Now this is just an example given by one paper here. So this is selective harmonic elimination, that you have 2 sets of the system. You have the V1 and is your 3V1. Okay, so this is your V1, this is your 3V1. So you have more panels for this inverter. So this, of course, this is of higher voltage, this is of low voltage. Okay, so this is a low voltage inverter, but they are connected. Okay, they are connected to grid, or this what is called as, it is a cascaded inverter. This is a cascaded edge bridge inverter. Okay, so combinedly they will produce the output. So combinedly they can produce different levels. Like your edge bridge was producing only VDC minus VDC or 0. Okay, so here we can have V1 and 3V1 can produce how many levels? 7 level. 1, 2, 3, 4, 5, 7 level. Okay. Sorry, 5 plus 9 level. Sorry, 9 level. Okay. So it can produce a voltage of 9 level. Okay. Now how the switching can be done? Okay, but because one is a high voltage, one is a low voltage. This is a low voltage, this is a high voltage. Generally we prefer the high frequency in low voltage and low frequency in high voltage. Okay, so accordingly we do the switching. So this is the waveform that is obtained as a combination of two edge bridges. So in one bridge which is of low voltage have more switching, and the bridge which has a high voltage has a less switching, and we got the combined waveform like this. Okay, so it is more close to sinusoidal. Okay, so it's more close to sinusoidal. So you have produced less harmonics also then. Okay. So you can have 7-level cascade edge bridge inverter, staircase waveform you can obtain, and then you can have to solve this kind of equations. Okay, you have to solve this kind of equation for that. And you have to solve it. Okay, you have to solve it. Then you can apply some advanced algorithms, advanced methods, neural networks and all to solve this. Okay. Okay, so this completes the selective harmonic elimination part. Okay. Then we can start the actually control of inverter. So you want to have a break or what we do? Okay. Any question till now for selective harmonic elimination, or any previous question also? Like, yeah.
You have shown a lot of switching, right?
Yes, sir.
In practice, do you achieve the switching perfectly, or you can be harmonic injected with imperfect?
Imperfect means we have to give some delay. That is,
I mean, these are because of this.
yeah, because when we are turning off the switch and turning on the switch at the same leg, you have to give some delay. The delay will give some imperfection, but very little. That
It's not noticeable.
much may not be, but still we can analyze that also. There are some paper on the analyzing the delay also. Because practically we have to give the delay because we cannot turn on the two switches on the same leg at the same time. So that introduce the delay. Yeah, microsecond, whatever, depending on the turning off time of the another switch. So here you can see the inverter which is connected to grid through a low frequency transformer. Okay. So this is a simple control logic. Okay. So this is a current fed inverter in which you are comparing the reference current and the actual current. So this is your actual current. Okay. Measured from this what you are feeding to the grid. Okay. And this is your reference current. Okay. And then you are passing it to you are generating the PWM waveforms. Maybe you need sorry, I have not shown here, it should be PI controller here. That will reduce the error. It should be a PI controller. And then how the reference is generated. Okay, how it knows that how much current it has to be fed. That will decided by MPPT. Okay, depending on that situation, what is the radiation level? Okay, okay, what is the temperature? Whatever is the PV curve. Okay, so that output, so whatever is the present condition of your panel, what is the voltage and current, okay, it is fed to the algorithm, and that will decide the what current need to be fed for to the inverter, from the inverter. That reference is given here. Okay, so the reference is, maybe this is a DC value, can be multiplied by sine omega t. Omega can be obtained from actually from this, maybe from the PLL, phase lock loop. Okay. So that will generate the reference sinusoidal signal compared with the actual value, pass it to the PI controller, and that generates the PWM signal. And that drive through the driver circuit, that will it will switch your inverter. Okay, and then that will feed to the grid. This is a simple system. Okay, but you require 3 PI controllers here. Okay, what is the problem? You require 3. It's very difficult to tune the PI controller. Okay, you are comparing the actual value and the reference value. Okay, then little bit complicated. We have to go for the DQ control. Okay, so we have to go for the DQ control, in which you have to use the Clark transformation to convert your 3-phase to 2-phase. Okay, 3-phase to 2-phase. Okay, parts will come in picture. Okay, this is a Clark transformation, and then so this is your
Are we still talking about harmonic elimination or something else?
yeah, we are talking about now something else topic, just the inverter control now. Yeah, so we have restricted the part of harmonic elimination to selective harmonic elimination. Okay, now we just talk about the what exactly the system is, what is the inverter interfacing system is to the grid. When you are connecting your panels, PV panels, the array of panel to the grid. Okay, so we are talking about the topologies first. Then I describe you the edge bridge. Okay, then I discuss about what exactly the symmetry. Okay, what exactly is the switching pattern, and what exactly the selective harmonic elimination technique. Okay, so now we move to the control of the inverter. Okay, in which you have to generate the reference. Okay, to compare with the actual values. Okay, so generation of reference is through MPPT. Okay, so this decides the what exactly it should work now. Okay, so it needs input. This is the output of your panels that is to be given to this. Maybe some more inputs it required, maybe temperature, maybe the radiation, okay, humidity, whatever may be, okay, depending on the method of MPPT. Okay, so it will generate some output which is used to generate the gate pulses to the inverter. Okay, so this is simple logic but not very stable, because you have to tune the 3 PI controllers here. Okay, so what is stable, that we'll more discuss. So stable is a DQ control. Okay, so for that you have to use the Clark transformation. You have to bring your alpha. So these are the stationary reference frame. Alpha beta are the stationary reference frame. ABC are moving, so you'll bring it to the stationary. So you take a projection of this ABC into alpha beta. Okay, so for this is your conversion matrix that you have to use, and then after that you have to use the Parks transformation. Okay, you have to have one more DQ axis which is rotating. Okay, D and Q axis. One is the fixed, alpha beta are stationary. Okay, and then this D and Q axis are rotating. Okay, with the frequency omega of the grid frequency. Okay, and you have to orient your voltage along the D axis. Let me see that those, yeah. So you have to orient your voltage at this D axis. So as if you are sitting on the D axis and D axis is rotating. So if you are sitting on the moving object appears to be stable. That is what the theory behind this. Okay, so what you are sitting on this D axis, that variables look stable, stationary. Okay, or DC value, or it is a DC value, not time varying variable value. It is better to control the DC component as compared to the AC component. It can be easily tuned. Okay, the DC component is not, they are not time varying component, so they can easily tune. Okay, so what we have here is ready. Okay, so okay, we can break for the tea. So just we complete this slide. We can discuss more also. So we have to convert this ABC into DQ. So alpha beta to DQ, and then you required here only 2 PI controllers. Okay, and that too for the DC quantities. Now this is your DC quantities, and what you are getting from MPPT is also DC quantity. Okay, so it will be easy, and then you can control your inverter. So we'll wait for the tea, okay, and discuss more about the next topic. Please join for the tea. हाँ ठीक है हो तुम्हारा हो
Pointer is better, sir.
हाँ right right
Online streamers can also see this.
right हाँ right okay but give who is the
Shubham sir has given. We'll give him to.
కానీ బాగా ఈరోజు
Did I call everybody? So we'll start the next session. Streaming is so as we discussed, so you have the inverter system connected to the grid through the low frequency transformer, and this is the control system. We are more focusing on the control system here. So we have the ABC component, the current that is converted into alpha beta component, and alpha beta is converted to DQ component. And this is actually, if you see in the waveform of the ID, you'll find that they are not varying with the time. Okay, so it is like a DC waveform. Okay, so it is very easy to compare and pass to the PI control that generates the error. Sorry, this generates the error, and then you get a control signal, and then you can generate a reference signal out of this for the as a PWM signal that can drive your inverter through gate driver. And this ID can be obtained from your MPPT controller. Sorry, this is a this is not a scalar base. This should be a DQ control. Okay, I have not changed this heading. It should be DQ control, not the scalar base. Scalar base was previous when we are not there is any conversion. We are just comparing it. Yeah, so this is your then non-isolated topologies. Non-isolated is just without transformer. Okay. But again, if you observe that the output of your inverter, DC to AC inverter, is also pulse waveform. Okay. Here also it is a pulse waveform. Okay. But what we are suppressing harmonics, and we are more prominently producing a fundamental. Okay. So you can directly connect it to the grid, but you may require some filter that you can connect the inductor or may not connect. Okay. But of course there is no transformer. Why transformer is not there? What is the advantage of having no transformer here? Because it is reducing the cost is increased if you are increasing a transformer. Efficiency is decreased. Okay. And the size you required more, space you required more. Okay. So let's not use the transformer. In one paper they have compared, okay, this without transformer, with transformer, and without transformer. Okay. So here, if you compare in terms of your weight, efficiency, and volume. Okay. So always you have the better efficiency for transformer-less inverter. Okay. So volume is also less. Okay. Weight is also less. Okay. And then volume is also less for the transformer-less inverter as compared to the inverter having transformer. So, okay, this is your, okay, I'll just keep this, is just understanding of your inverter. So this was the part of a PWM technique that we used to teach to the MTech students. But I will give you the presentation, you can also study, but this is not much part of the discussion today. Okay, so we'll move to the next presentation. One more is there. I have downloaded 2 presentations. Oh, again, open my account. This sorry, GAN schedule हो गया अभी. हाँ, this leakage current, no? Leakage current. So now we'll study what is the problem when you are in the operation of the inverters. One of the problem is a leakage current. Okay. Most prominent problem, or what we can say, the failure of inverter. So we also face the failure of inverter. I can Shravan Kumar may focus on that we have failed some inverter, and most of the reason of failure is the capacitor. Okay? The capacitor fails, and that's why the inverter is also fail. Okay. So the most deterioration element that goes more deterioration is the capacitor in the inverter. Okay. So that we'll also discuss, but let's discuss the leakage current mitigation first. So okay, so electrolytic capacitor, coupling, DC-link capacitor. Okay, so this is what we discussed already. That was also in this presentation. So we have transformer-less inverter with boost or without boost. So what is the problem with when transformer nahi hai to kya problem hai? Okay, so we have the problem of leakage current. You can find out it forms some circuit, okay, that can flow the leakage current. Okay, that can flow the leakage current because there is no any galvanic isolation. Okay, we'll again come to this point. This is the diagram. Okay, so understanding the leakage current in transformer-less system. So the safety concern, the leakage current over 300 milliampere only, okay, must trigger a break within 0.3 seconds as per some standards. Okay. So if leakage current goes to 300 milliampere, it should break within 0.3 seconds. That's what the grid standards. Then why it is caused? It's caused by the parasitic capacitance between the PV panel and ground when common mode voltages varies. So what is this common mode voltage? What is parasitic capacitance? Okay, that we are going to study. Then it requires the protection requirement. Updated German code requires leakage current protection device in accordance with IS standard. Then we have to suppress this leakage. How we suppress? It is achieved through the topology design that maintains constant common mode voltage or provide decoupling network. So the two ways that we can suppress this leakage current, one is constant common mode voltage. Why it should be kept constant, that also we'll see, and provide decoupling network. So we have to decouple the thing because there is no isolation. So at least with the help of switch, you can decouple the PV system with the grid for some momentary duration. Okay. So how to do this? How to achieve this? First, we'll study the origin of parasitic capacitance in PV system. So the parasitic capacitance arises due to the electrostatic coupling between PV panels, have the conductive surface like metallic frame or backside of the solar cell, and earth ground. This act as a dielectric capacitor. Okay, so here you have the earth cell that has at some potential, and then you have the ground connected supporting system, frame and all. Okay, so that in between it forms the capacitance. PV modules are made of semiconductor layers and metallic contacts, usually mounted on the metal frame. This frame on or the back side of the PV panel is electrically floating, but physically near to ground. The insulating insulating, encapsulate, and air between the panel and earth act as a dielectric medium, forming a capacitor. Okay, so air also act one part of this. If the humidity of air increases, that capacitance will increase. Okay.
What is the reason why you can't ground the panel,
Yeah, you can ground the panel. You can ground a supporting structure,
but not the panel?
not the panel. Panel means you can see there is a positive and negative of the panel. So this is your panel. So this is your positive and negative of the panel. Only there is a supporting structure. So that is grounded. That is already grounded. It is on the ground. Yes. Okay. Or we are providing a special ground wire also. You have the ground pit.
Yeah,
And you are connecting it here.
but the panel itself has got,
But it generates a capacitance. So there is a cell, solar cells are here. Okay. How many number of solar cells? So it forms the capacitance, okay, between the cell and the, very interesting thing to know this. So if you have a panel, so it forms a capacitance like this. So they are all distributed actually. All these capacitance are distributed.
so even if you ground, there is a capacitor between the cell.
Cell and the panel, because support, this is all support, okay, the glass and all, it is supporting the cells. So what is the exactly cell and their support? In between them there is a capacitance. That is a parasitic capacitance. Inherent. We cannot do anything with this. See, the panels are spread in a huge area also. That also increases its capacitance. The distance. Okay. So it is huge in in terms of huge area, in terms of acres of land. Okay. So PV modules are made of semiconductor layers and metallic contacts, usually mounted on a metal frame. This frame or the back side of the PV panel is electrically floating. Okay, we have done this. Okay, so this results in parasitic stake capacitance, typically around 50 to 200 nanofarad per kilowatt peak. Okay. During inverter operation, common mode voltage variations excite these capacitances, causing leakage current to flow. And then it generates across this capacitance, there can be a common mode voltage. Okay, so that triggers the current. Okay. So when the current will flow in the capacitors, what is the current in the capacitor? C dV by dt. Okay. If voltage change, then only current will flow. Okay. If voltage is not changed, current will not flow. dV by dt is 0 when the voltage is not variation. There is no voltage variation. Okay. But when because of this change in the voltage, okay, the current will flow. So in one of the papers, this is what they have given, that they have the water and in water molecule also form the capacitance. Okay. Then there is a frame C3 and C2. So roof surface is shown. Excuse me. Put F5 here. So leakage capacitance value depends on many factors: PV panel and frame structure, surface of cell and distance between cells, module frame, weather conditions, humidity, dust or salt covering the PV panel, then type of electromagnetic compatibility, EMC filter. So this is how the leakage current flows. So the factor affecting stake capacitance are dust, humidity, surface of PV and ground frame, and distance between PV module and PV cell and module. The parasitic capacitance is charged and discharged by common mode voltage, which give rise to leakage current or common mode current. It is threat to the safety of the personnel handling the PV and increases the current ripple in the grid. It increases the electromagnetic interferences and overall system losses. Now the system is shown here with transformer. Okay. So it is not only parasitic capacitance which is shown here. Okay. Excuse me. So it is not the parasitic capacitance which is shown only here, but it is shown here. But there are other capacitances are also there. See the capacitances between this terminal and the ground. So this capacitance with this terminal and ground. And you can see here the transformer, okay. Transformer also has the interturn capacitance, okay. So that may complete the circuit, but interturn capacitance are very small, okay, and that offer very large reactance to flow of current. So that's why transformer offer the isolation, okay. So there is no any flow of leakage current when you are using the transformer, okay. So when you are not using the transformer, then there is a direct path available to flow the current, okay, leakage current. So the common mode current ICM is negligible through the system with transformer connection. This is because the presence of the stray capacitance in the low frequency transformer. And these capacitances are in the order of 100 of picofarad, and then they exhibit a high impedance in the low and medium frequency range. So there is no point of discussion when you are using the transformer. So there is no issue of leakage current. Okay? But why you want to avoid the transformer? To increase the efficiency, to reduce the cost. So transformer is also additional element that you have to maintain. Okay? So that's why you want to remove the transformer from the system. Okay? But it caused the issue of leakage current. Then safety and operation issue with the leakage current, undesirable tripping of the residual current protection system, deterioration of electromagnetic compatibility, decreasing PV module lifetime, harmonic distortion of the current injected into the grid, and electric shock for person touching PV panel. So having the galvanic connections, we can remove this issue. Then again we have again look toward the unipolar and bipolar PWM. Okay, in leakage current point of view now. So this is a single phase voltage source inverter, again as the same slide as we have discussed bipolar PWM. Okay, and so there is no zero voltage. Okay, there is no any zero level voltage. You can have the plus VDC, that is VAB is either 200 or minus 200. Okay, depending on what the source voltage is. But in the unipolar, you have the negative voltage, zero voltage. Okay, in the positive half waveform, you have 200 0, and in the negative side waveform, you have the minus 200 and 0. So if you compare this unipolar and bipolar, okay, so in terms of let's say harmonic contents, you have higher low frequency harmonic in the bipolar. Okay, you can see the point harmonic contents here. You have the higher low frequency harmonic in bipolar as compared to unipolar. In the unipolar, you have lower harmonic distortion. So in that sense, it is better. Okay, bipolar is not better, or unipolar is better than the bipolar PWM technique. And then switching losses is also higher in bipolar, because it is switching from minus 200 to 200. Okay, and here in the unipolar, it is switched from 200 to 0. Okay, that meet more switching losses in bipolar. Control complexity is simpler in bipolar. So THD is higher as compared to unipolar. efficiency is also lower in bipolar as compared to unipolar. Then we should go for unipolar or bipolar. So this is how now let's analyze the common mode voltage for this edge bridge inverter. Okay. So we have a simple edge bridge inverter connected through a DC source. DC source can be a PV system, PV module. Okay. And then you have L1 and L2 are the filters connected in the phase side and neutral side for eliminating the harmonic. And then there is a grid VG. Okay. And then you have the switching function like alpha 0, alpha and beta is used as a switching function. For leg 1, alpha is 0 means S1 is off and S4 is on. If alpha is 1, S1 is on, S4 is off. And beta function is used for the second leg. So beta is 0 means S3 is off, S2 is on, beta 1 is S3 is on, S2 is off. So you have so these are the parasitic capacitances. Okay, parasitic capacitance also formed with the negative terminal and positive terminal both. Okay, so you have the two parasitic capacitances. And then one additional resistance is here. The ground resistance is added here just for analysis. So this is an equivalent circuit. Okay, if you assume that the function that is operating VAC and V. So this is your common ground. VC is your common ground. C is your common ground. So what is VAC and VBC? Okay, so if you have two function VAC and VBC, it is reduced to VDC alpha T and VDC beta T. And then if you simplified, how you simplified this? I have written directly, but you can apply the simple superposition theorem. Okay, you can see there are three sources here: VDC, okay, then VAC and VBC, and grid. Okay, so you can form the circuit, simple equivalent circuit, by applying each source one at a time and adding the equivalent source. So what you will get is VCM. And L is your equivalent impedance. The value of L is this L2 L1 by L2 plus L1. Okay. So once the circuit is completed, there is a formation of current. So what VCM, this is the common mode voltage, depends on this VAC and VBC. So VAC is alpha VDC and VBC is beta VDC. So this is what your VCM. Okay. And this is the capacitance, total equivalent capacitance. And why this current will be there? Because VCM is changing. If VCM is constant, current will not be formed because capacitor will remain the charge. Unless and until VCM is changing, not changing, your leakage current will not form because current in the capacitance is C dVc by dt. If that voltage across capacitance is constant, no current. Okay. So what our job is to keep the common mode voltage either 0 or constant. Okay. So let's see now bipolar PWM. In bipolar PWM, you have alpha and beta either 1 and 0, and for which your VAB and VDC, VAB means voltage across this A and B point is either plus VDC or minus VDC. And as per this equation, your VCM is always VDC by 2. If you substitute alpha 1 for this condition, alpha 1 and beta equal to 0, let's say your L1 and L2 are same. Okay, if L1 and L2 are same, then your VCM is VDC by 2 for this situation, and also same VDC by 2 for this situation. But if you are not having L1 and L2 same, okay, then there will be leakage current because these two will not be same. Okay, so when you have L1 is equal to L2 for bipolar junction, there is no change in the common mode voltage and there is no leakage current. Let's see the unipolar now. So when it is a unipolar, you see now in unipolar you have additional switching when both are 1 or both are 0. In bipolars, there was no such case because there was no zero level. Now in the unipolar, you have zero level. So for the first case, same like your bipolar, the common mode voltage is VDC by 2, VDC by 2. Now it will achieve this state also in which your VCM now become VDC. You will achieve this state when either top switches are on or bottom switches are on, you will achieve the voltage 0. So inverter is going through all these states and that makes the change in the VCM from VDC by 2 to VDC to 0. Or again jump to VDC by 2, VDC 0. And that caused the leakage current. Okay, that caused the leakage current. So what is the trouble? When there is a leakage current, now you have the appliances like you have refrigerator, all the appliances are connected to the ground. You have the ground wire, okay? You have the 3-pin plug, one is a line, neutral and another is the ground. So that ground is connected to the appliance ground, okay? So even if there is a leakage, any small leakage, any damage to the insulating part of the devices, okay? So that will go in the ground. So even if you are touching the fridge, okay, so you are safe because already the path is available to the leakage current that will flow to the ground. Okay, in summer days in the Nagpur we have the coolers that we are operating. Okay, so we have the many news that because of the electrocution, that shock, several people dies. Okay, so either they don't have proper grounding system, okay, and there may not be ground connection. There may be only 2 phases that you are using, okay. So always the chances of leakages are there because the old coolers, okay, damages of insulation is always chances are there. So for safety operation, you always have the ground and it works. So when this ground is not there, let's say this ground is not there and some part is damaged, some insulating part, some winding is damaged, some insulation of winding is damaged, okay. So that will touch to the appliance, okay, and only path is available through our body if this path is not provided. But again, there is one more protection in ELCB. What ELCB detect? It will detect difference in current. In difference in current is phase and neutral. If it find a difference in current, it will trip the circuit. Means current is going to something else, not in the device. Okay, so it will detect that there is some grounding. So it will trip. So this is a protection now. It's very much compulsory by the government to each new apartments and buildings and homes. So you have the system and how the current flows. Okay, how the current flows. So you have, okay, that will come in the next. Now you have the PV system. Okay, you have the PV system connected to the same line and neutral. So because of this, so there will be additional current is flowing. So you have additional current flowing in either of the wire, and that will be detected by ELCB as a fault. And that will detect the ELCB and it will trip. So that's why you should have a very minimum leakage current or no leakage current in the system. Now when there is a transformer, there is no point. So complete system is isolated. Okay, complete system is isolated. Now one more problem is when you have such a case, there is no leakage current. Okay, there is no because there is no path. There should be some path. Okay, from this ground to this ground. So that is not available. So in the previous case, path is available. Okay, path is available to this. Yes. Now there is no path for leakage current. But now again the capacitance remain charged. Your parasitic capacitance remain charged in this case. So what is the problem if it remains charged? Then if you touch the system, okay, you will get a high voltage shock. Okay, current will flow through your body. In this case, you have to ground one of the terminal of the PV panel, either positive or negative. Once you do this, always capacitor will get discharged. Okay. But when you have the, so when you have, will do this, when you have the transformer, okay, so you can directly connect one of the panel, either positive or negative, you have to ground it. To avoid that, so now if you are touching, the path is available, so it is already grounded. So this capacitance is already grounded. Okay. And again, as we discussed, there is an interturn capacitance, so there is no leakage current possible to the transformer. Because of high impedance, so impedance is 1 upon omega C. C is small, so impedance is large. And omega is small, particularly. Sorry, omega is small, that's why the impedance is large. The problem with leakage current causes severe electromagnetic interference. It gives a grid current distortion and introduce additional losses in the system. So this is the main thing that we want to avoid. So as we look here, so if it is a bipolar PWM, you have the common mode voltage which is constant, VDC by 2. And then there is no leakage current. If you have a unipolar, then there is no constant common mode voltage, then there will be leakage current. This is what we have seen with derivation. Now there are H5 inverter. What it does, we have additional switch, so it is H5. So fourth switch. Okay, so these are 4 switches, regular switches. In addition to that, this is the 4th switch. Now when these 2 switches are on, the voltage is positive. Now if you want to apply unipolar PWM, okay, so when 2 top switches are on, so here in this case your voltage is with the parasitic capacitance is become some voltage VDC by 2. Okay. Now when you have generating the 0 voltage, this S5 is turned off, that will isolate the PV part and this part. As it isolates, there is no change in the value of voltage across the capacitance. There is no path to change the voltage. There is no path to change the voltage. So this voltage will remain the fixed. So there is no any chance of leakage current flowing in this system, because we are isolating the system. Okay, that is a H5 inverter. Okay, so with H5 inverter, you can see the common mode voltage is VDC by 2. Remain constant, not changing. So no common mode, no leakage current. Then there is a H6 also, one more switch is introduced. So why to turn on only one switch, turn off only one switch? Okay, so just to reduce this stress on one switch, you have additional switch. So either this is off or this is off. Okay, so that will separate, or both are off, that will separate out the circuit. Okay, and there is no flow of leakage current. So you have to break the path. Then there is so this was the DC coupling. You are coupling the DC side. Okay, what we discussed the technique that you are coupling the DC side. There are few techniques that you decouple the AC side. Okay, you are decoupling the AC side. So this is the technique, that is a Herrick inverter. It's given in this paper. That is highly efficient and reliable inverter concept, in which you are decoupling the AC side. How you decouple it? Give the example. Yeah, here it is. So when you have the 0 voltage, okay, so in this diagram, then when this either this top or if you want to produce a 0 voltage, okay, so these 2 switches are on. So these 2 switches are on, it will produce a 0 voltage across the grid, across the load, okay, and all the switches are turned off. So there is a complete isolation between PV side and your grid side. So this is your AC decoupling. Okay. So this is a Herrick inverter technology. So this what about the inverter that either you can select a particular PWM technique. So what we select, we used to select a bipolar PWM, but bipolar PWM will generate more THDs. Okay. So if you want to select unipolar, then you can go for H5 or you can go for Herrick. Okay. So that will solve both the purpose, that will reduce the harmonic also, and that will also reduce your leakage current in the system. Another problem that, okay, any question till now? So we can start with the next topic, that why inverter failure. Okay, as we just, so there's a most chances of failure is a failure of capacitance. That is aluminum electrolyte capacitance, AEC. The life of solar panel is almost around 25 years. That guarantees from the manufacturer that once you install, it will work for 25 years. But inverters are less reliable and typically have only 3 to 7 year lifespan. Even if you are not maintaining it, it will failure earlier than what the life is. Beyond this high failure rate, inverter failures are reported mainly due to aluminum electrolyte capacitance. Then the chances of switching semiconductor devices that fails or inductive element fails. The primary factor which limits the life of converter is AEC, that is aluminum electrolyte capacitance. It is responsible for about 60 to 70% of the total failure. This value is expected to be higher from string, low medium power solar PV inverter due to exposure to high ambient temperature. So we have huge temperature in the month of May, April. Okay, this month April was more high temperature, ambient temperature. Okay, more sunny days we observe. Okay, and we observe that we have several inverters got filled, and we have floated another tender to replace that inverter. And I tell you, there is no system that to check the inverter. So it's very interesting area to work with. There is no system or there is no facility in India to check the solar inverter. Even some manufacturer claim that this inverter is operate MPPT. That also we don't verify whether it is really operate MPPT or not. So there is no such system. I don't know whether in Australia do you have such system for inverter, for testing of inverter.
Testing, but maybe not every.
No, not in every inverter, but some lot inverter. But how do you test then? Because unless there is some site that it should work, how it can be tested?
Yeah,
Or how do you test the MPPT, whether it really work with MPPT or not?
we have got a lab where they come and check. So they do that because when they want to get the certification,
Okay.
they have to show the test. So we have got a lab where they come and do the test. I am not directly involved.
Okay. You have the facility then. Okay. So why we require DC link capacitance? Okay. So you have the inverter which is connected to a PWM inverter and then connected to the grid. So can I remove this capacitance in between? Why we require this capacitance? It's called as DC link capacitance, and that causes the more chances of failure. Okay. So if you derive the expression of what you are feeding to the AC grid, okay. So what you are feeding to the AC grid is this: V peak I peak upon 2 minus V peak I peak upon 2 cos of 2 omega t. So you are feeding the power which is a constant in nature as well as pulsating in nature. Okay, what you are feeding to the grid is constant power as well as pulsating power. And to obtain this, and your inverter and your generator or your PV system can only produce the constant power. So who will produce this pulsating power? It is only because of the capacitance. So you require this capacitance to generate the pulsating power. Okay.
Why is that pulsating power?
So it is a derivation, sir. If you derive this what you are feeding to the inverter, you have a pulsating power plus average power. And this pulsating power has a twice the frequency of the grid.
Okay, that is simply AC system power.
Simple AC system power transfer, that P is equal to Vm sine omega t Im into Im sine omega t plus phi. But if you assume that power factor is 0, then it is Vm Im by 2 into sine square omega t. So if you solve it, it becomes your constant power and pulsating power. So that comes out to you. So who will provide? Because your inverter, your PV panel cannot produce the pulsating power. So that's why you require the capacitance. Okay. So that's why there is a need of capacitance here. So this is the main instantaneous AC power supply to the grid, and this is the time varying oscillation of the AC power that is produced through the capacitance. And as we derive the value of capacitance. So the value of DC dealing capacitance is S upon 2 omega G VDC V. And so it depends on the rating of the inverter, then DC input to the DC input voltage, and the pulsating voltage, permissible voltage ripple. So value of capacitance, so more rating of the inverter, more value of capacitance. Okay. But if you increase the voltage rating, then your value of capacitance will reduce. Okay. If you increase the voltage rating, your capacitance value will reduce. If you reduce the voltage ripple, then again you need to have more value of capacitance to be connected. So more value of capacitance, the failure is more. Okay, more failures. Okay. There are some alternative to aluminum electrolyte capacitor, like a derated aluminum electrolyte capacitors. Means you are putting some higher rating of capacitance, so the stress actually, what it actually take, it is more capable of taking more stress, but you are applying less stress. But again, the cost will increase. Then a solid film type AC capacitance. The derated AECs refer to AECs that are operated below their maximum rated voltage or current to ensure reliable performance, especially at higher operating temperature, thereby improving reliability. Then solid film type AC capacitance also offer high reliability as compared to conventional AC. However, size and cost of these alternatives are higher than those with what we are using right now. The existing solar inverters are based on voltage source inverter topologies. And considering the high current ripple supplied absorbed by the DC link capacitor in the voltage source inverter, large value of capacitance is required to limit the voltage ripple across the solar PV inverter terminals. Therefore, alternatives suggested above may not be economical viable. So again, the market is driven by the cost. So always we prefer the low cost. Even what we have the tendering. So we have to choose the lowest, whatever the inverter that the manufacturer is supplying. So we choose always the lowest value of the manufacturer. Yeah, then there is a last topic maybe, whether to go for current source inverter versus voltage source inverter. 1 minute, I missed some diagrams maybe. Yeah, the current source inverter. Okay, no diagrams. It would have easy for me to describe from the diagram. Yeah, there are current source inverter and voltage source inverter. In the current source inverter, you are producing, actually there is no such current source inverter, but you have large inductor that you are connecting. Okay. to the voltage source that generate a constant current, okay? And then you can have the current source inverter. So what is the advantage of this? The most of the ripple that is absorbed by the inductance. And then you have the reduced value of capacitance. So the life of current source inverter is higher than the voltage source inverter for the PV system. Okay. So because what you are doing is you are reducing the electrolytic capacitor value of, because the most of the stress or ripples in the system are taken care by the inductance. Okay. So that is only the point for. And one more thing, one more advantage is it is also amplifying the system because it is acting as a boost converter also. If you remember the circuit of boost converter, there is an inductance and that will boost the voltage. So here is also there is a boost inductor and that will help in amplifying the voltage. So these two advantages are there for the current source inverter. It stopped. We have given the limit and it stopped. It's okay. I think we have finished. No problem. So that was the last topic. Maybe if I have a diagram, I can share it to you. Maybe I will add, and that presentation I will share to you. I don't know how I missed that diagram. But that is only the thing. If you remember the current source inverter, it is. So there is a large inductor here that makes the current constant here. So if you use this, the value of most of the ripples are absorbed by this limit. So you will have the reduced value of receiving capacitance. So that is only the case. It is coming to streaming. Okay, it's okay. I think it was stopped before. Okay, no problem. Any question if you have related to, if you have suggestions also please, based on your experience and what you have read maybe surrounding this or related to this, please share.
How much does the capacitor cost?
Capacitor cost, I cannot say. I don't know, sir.
The failure point is capacitor.
Yeah, we should have better quality of capacitor, but again, it may have increased the cost. Thank you. Okay, that was only the thing. So thank you. If you have any question, or we can have more discussions. Maybe you want to say something? So tomorrow in the afternoon session, because two presentation already continued today, so maybe tomorrow in the afternoon session you will be having tutorials. So you'll actually maybe involved in the simulation of this bipolar unipolar PWM and also the leakage current. Okay, thank you. Thank you. So we have the end of the session today. Thank you.
will meet with